Yeah, so to get started, I'm going to talk about new approaches of 3D vision. And basically, the topic in itself is very old. I think most of you are aware that 3D vision is instrumental to a lot of industrial applications, ranging from robotics to automation to quality inspection. And the need for 3D vision is ever increasing due to higher demands on autonomous systems in production of small lot sizes. And what we've seen previously is that almost everything has been possible with computer vision, and most of you have been working in this or related field and know very well that a lot of tasks that were previously not possible or had to be carried out by humans can nowadays be very efficiently done by computer vision systems. But very often these systems are very expensive to set up. It takes an expert to do this. And this is why we see that a lot of solutions are very expensive to the end customer. And this then leads to a lot of applications that cannot be solved with 3D computer vision. Not because the task in itself is not possible, but because it's just too expensive. And this is what I wanted to show here on this slide. Basically, we can solve almost every computer vision task. We can have the Hubble Space Telescope to look back into the distant future or distant history of our galaxy. But it is so expensive that it's only possible by a conglomerate of governments to do something like this. Yes. And this is what we also see on the shop floor, that very often it gets, the solution has to be adapted to the application at hand. And if you have a small lot size, it's not feasible or just gets too expensive. On the next slide, I wanted to take everything back in history. And wanted to talk about EMVA cameras. So the basic theoretical or technical advances of light field imaging, which is one topic I wanted to talk about today, is basically the light field is the complete optical information that we can capture with cameras. And the idea is not only to capture the 3D information with one sensor, but to use multiple cameras. The idea is to look at to capture the light field, so to capture the optical information with an array of cameras. And this has been done by Ives in his patent of 1903. So we want to talk about the future or the new advances, and we look back into the distant history. Over 100 years ago, Ives developed a camera which was an array of pinholes, which he used then to take images and capture visual information or capture 3D information with such a system. If you go to the next slide, there is a small picture of this. So this is an image from his patent, and you can see that there is a lens that captures the light, and then this is then imaged on the image plane using an array of pinholes. And the idea was then shown on the next slide. You do a multiplexing in space. So basically, as you can see, the images are captured from each of these pinhole cameras on the film. You have a sensor pitch, basically, or pitch of these pinhole cameras by a distance of b, and this then allows you to capture all these different views of the scene, so all these different views of the environment onto a single imaging plane, and all of this together describes the complete 4D radiance of the scene. And this is, of course, an extremely powerful and innovative approach, yet it was limited by the use of pinhole cameras. And this was then improved, and his idea was then to use these basic principle of Ives camera and then bettered on the problem of these pinhole cameras by introducing lenses, and this is shown on the next slide. So again, he does space multiplexing. He has replaced the pinholes by real lenses, and this is then what we know today also as light field cameras. So it's cameras that capture the visual information from different views at different locations. And this is basically what was done by Lippmann some time ago. If we then go to the next slide, we can see more modern planoptic cameras. Here you can see the very first advances in 2005. So Kodak, for example, that is 60 megapixel sensors, and they could also introduce micro lenses, as seen on the right-hand side, to then capture 14 by 14 light fields or views of the light field with a resolution as is shown there. And the basic principles is also shown on the next slide. So this is an image of a bigger lens array, basically. And what you can see here is very nicely the different locations or the different views of a scene. This is basically a lens array. And you can see that indeed each of these different views, you can see the scene from a slightly different location. This is then a sampling basically of the light field. So we not only see the intensity of the light as it's coming from one direction, but we can also see the different views, so the different directions the light is coming from, and we can then move this around in space and in this fashion capture the complete light field. On the next slide, this is shown in a more modern setting. So here you can see a microlens array as it can be introduced directly on the CMOS sensor. And on the next slide, again, you can see such a raw image. What is shown here is basically a scene, and it's fairly difficult for each of you to really make head and tails out of this. So basically, this is the raw image of the micro lenses, and if you move really closely to your scene, to your screen, then you can see that each of these different micro lenses then shows you a different view of the scene, similar to what we've seen in the image before. So basically, the capture process of computational photography is shown on the next slide, where in old technology or in previous technology, you had to only capture an image and you had to have the image directly on the sensor. And this is now different in that we introduce, for example, a micro lens array between the sensor and the lens, the main lens. And then we need to introduce some processing to complete the view out of this. So basically, the raw information needs to be processed in order to get the information out of it that is required for a given application. And this is then shown on the next slide. We get not only an image, but we get these microlens views, and then we can use computational imaging, seeing these computational computing out of these different views, for example, things such as 3D information or additional information about a scene that is usually not captured by the imaging process. On the next slide, this is shown in an application. So basically the same image as before. If we now turn on our computational processing, you can see on the next slide the real image that was seen. So this is a girl taking a picture herself. And now if we go back and forth through the next few images, you can see that if we do the processing a little bit different, we can change the viewpoint very slightly. So I'm not sure if you can see this. But you can see that we can go back and forth and we change a little bit the viewpoint, or we can go even further and change the focusing plane. So we can choose not only where we are viewing from, but we can also choose what has been focused on. And this is, of course, a very nice feature of these light fields. We do not capture the scene as we did in standard photography, and then we cannot do anything about it anymore, but we capture more information, we capture the complete light field. And this allows us then to do something after the fact. So we can do much more with these images or with this data as was previously possible. So then if we turn to the next slide, the question is, of course, how do we capture the light field? There are different ways of doing this. The first and most simple one is doing a sequential capturing. So we do not do the spatial multiplexing as has been shown by Lippmann or Ives imager before. But we can just use a normal standard camera and then use a gantry setup or a robot to move it around a scene. And this allows us to do very high resolution captures of a 3D light or of a 5D light field. But of course, it is very very time consuming. It's very slow, and it takes a lot of time to do a full capture because we have to move the camera around all around the object and do a fine sampling of this usually. So this is not really feasible for a lot of applications, particularly not in the field of quality inspection or industrial applications. So much better are ways of doing spatial multiplexing, as you can see on the center image. So there we introduce a microlens array between the sensor and the main optics. And this is very inexpensive and very fast. But of course, the resolution is much, much lower as compared to the sequential capture. And of course, images like this are commercially available. So for example, here in Germany, Radfix offers systems like this. And previously, Lightro in the US used to offer something like this in a commercial or in a consumer application. Another way of capturing the light field is shown on the right. So we can, of course, on the right where we see camera arrays. So very similar to the way that Lippmann's camera worked, we can just have a sampling of images of the light field. So here is shown the Stanford array, which is one of the first systems of this kind, where they used a large number of VGA cameras to capture the light field. And of course, this gives you the advantage of having very high resolution. It is very fast, and you are very flexible and have large baselines. But of course, very often it's expensive and it's difficult to calibrate or bulky. And this is shown here on a small version of this. For example, a 4x4 array was built by Pelican Imaging, and they were able, or they wanted to introduce this into mobile cameras, for example. Okay, so what are the advantages of using this light field capturing or light field imaging in real applications? So I wanted to show you some examples of this. On the next slide, we can see, for example, super resolution. This is an approach where we capture not only a 2D view, but we capture the whole light field. And then if we do this, we can improve the resolution quite significantly. If you look on the top left corner, you see the image as it's captured by a normal 2D camera. And if you then use the information from the light field, so from the other camera views, we can use super resolution and increase the resolution by a high number of factors, depending, of course, a little bit on the data that you're looking at. And so you can use the additional views for increasing the resolution. And this has some applications in quality inspection, for example, where you can use this to visualize smaller defects than previously possible. On the next slide, this is more the topic of 3D. You can use these different views for generating 3D information. So shown on the left is the center view. So this is just one of the images that were recorded by a light field array. And in the middle, you can see a depth is measured from a stereo approach. And you can see that particularly on glinting parts of the scene, left is a stone, for example. Wherever there are glinting or complex optical properties, you can see that stereo fades in these settings. This is much better on the light field 3D measurement, as you can see on the right-hand side. If we then go to the next slide, we can see that an object has more information than just the geometry, but we also have glint properties, or we have the color information, so the texture of the object. And all of these features can be measured by light field imaging directly from the light field images. And then the information can be separated and used for different parts of quality inspection, for example. Because the topic is not new, also some large companies have turned to this really innovative technology. If we look on the next slide, we can see an example of such a light array by Google. This is part of the Google Light Fields group. You can see they're using a sensor array put on a sphere, basically, on a virtual sphere. And what they are doing is they are capturing the light field of an indoor scene of the space shuttle, for example, in this case. And they can turn this, so they do a combination of spatial and temporal sampling of the light field. And they use this to capture indoor scene, for example, and then using the separation of information of geometry and of color to then building immersive videos out of this. On the next slide, you can see an up-to-date approach. Here they use, this is a paper from SIGGRAPH of 2020, so of this year. And you can see on the left-hand side a capture rig, which is a sphere, or they use commercially available consumer cameras. They put them onto a sphere setup, and then they use this information for capturing dynamic scenes, such as shown in the middle. So this is a person with a flamethrower, and they are capturing this information and building immersive video, capturing the 3D information out of this, and turning this into really immersive videos. So if you have some time available, look up this paper. They have a very nice demonstration of this technology on the website, where you can then really use the experience either with a VR headset or using your mouse and pointers to rotate the scene and moving in the scene in 3D space. So what you can see from this is that this is a technology that is very powerful, that has a lot of applications, and that's also used by a large company. But mainly this technology has been used for generating content in the terms of videos or computer games and computer graphics. What it has hardly been used for is for industrial applications. So I've mentioned the company Raytrix. Most of you are aware of them here in Germany. And they are, of course, turning these principles to industrial applications, but they are among the only ones doing this. At HD Vision Systems, we have also developed a system of for capturing light field imaging, and I'm showing this on the next slide, where we have built a 3D sensor capturing light fields in a spatial sampling way. So we have decreased the number of cameras to sampling the light field in a cross-shape pattern, and this allows us to capture the most significant part of the light field. And this allows us to then have very superior results in terms of 3D capture and in terms of quality inspection for performing things such as I mentioned, such as super resolution or separating glint, color, and textures and shape from the objects. And we can then use this for all kinds of automation, robot controls, and quality inspection. On the next slide, you can see some other examples of such capturing devices we are using. On the left-hand side is a one-camera system, such as a gantry setup, as I've shown you before, but more importantly, also sensor lines as in the center, or arrays such as the LumiScan X, as we termed it. And we are using these in different applications for quality and control, 3D capture, and measurement. Basically, as you can see on the next slide, we want to enable human-like machine vision using all these computational imaging aspects as I've mentioned before. So basically, we are using this small sensor, which has a size of about 13 by 13 centimeters, on robots in automation tasks, mainly for automotive suppliers for dealing with all the challenging quality inspection tasks. On the next slide, I have compiled a little bit the advantages of this computational imaging and 3D measuring technology. Basically, we are using computational imaging for industrial applications. It is very independent of external conditions or lighting conditions. It can be used in normal room settings. We do not require any special illumination. It is very precise, even on shiny objects such as metal. And this makes it predestined for quality inspection and deployment in manufacturing of metal objects, for example. It has a high multifunctionality, meaning we can use it for quality inspection, we can use it for higher resolution tasks, or we can use it for capture of 3D information. And it's very flexible. We can use it with different sensors. It is very agnostic to the capturing device that you use. So we can use different 2D cameras for capturing the night field and apply our algorithms of computational imaging directly to these applications. Of course, nowadays, as you're all aware, and some presentations later on today are going to talk about deep learning and quality inspection with machine learning. And this is, of course, something that has revolutionized the field of industrial image processing also. And of course, we are also using machine learning for all types of quality inspection. And the advantage of using light field imaging in this setting is, of course, that you have much more data. You have much better sampling of the scene, and you can use all this information as the light field for deep learning, so for training the networks, and then for the inference later on as well. Let me maybe skip the next slide and go to the slide after that. I want to show you some results that we are using for light field capture. So basically on the top row, you can see separation between glinting objects and the texture in the top row. So you see a complex scene of a metal object. Using light field imaging can be used to separate glint and color of these objects. And this is, of course, very interesting for quality inspection. So you can look at the glint properties if those surfaces have been machined properly, but you can also look at the texture and see if everything there is according to order. And in the lower part, you can see a 3D point cloud as captured by our devices. And you can see that they are very high resolution and very good quality of the point clouds. And these are, of course, also metallic objects. So also objects with very different or difficult optical properties. Going on to the next slide, I wanted to show you a little bit of the partners we've been working with. Shown here are companies in terms of automotive suppliers or OEMs themselves. And shown here is an example where we use the sensor handheld to measure a complete car scan. And this, of course, also shows you the limitation of the technology. Basically, it's a surface measuring technology, so it cannot be used for measuring glass, for example. And this is why we do not have any data on these glass properties or directly on the mirrors. Going to the next slide, I just briefly wanted to show you that this technology can nowadays be deployed directly on the robot or mounted on the end effector, and can be used for bin picking tasks, for example, or quality inspection tasks. Of course, I wanted to take a brief moment also on the next slide to compare this technology of 3D measurement to other technologies. So here you can see the LumiScan sensors using different optics, for example, so having different working distances. And we've compared this to some of the best sensors available, talking about stereo systems or active stereo using pattern projected. And on the right-hand side, you can see basically a toy scene that we have used for measuring. So you see metallic objects, you see glinting objects, you see transparent objects or objects used in applications such as PCB. And on the next slide, you can see a little bit of the results. So you can see that standard technologies such as active pattern projection, as shown here from the Insensor, are very good already. They have a very good accuracy, but you can see that the data is not very dense, basically because you have reflections or you have occlusions where you cannot have any measurement. And on the bottom right, you can see our technology. So the accuracy is a little better than shown on state-of-the-art systems. But the point cloud it's much more denser and has much better data used than for tasks such as bin picking or quality inspection. With that, I'd like to conclude and open up to questions and answer.